This is the Math 2 lesson summary video for leap year. Leap year is the fourth task of Unit 1. The purpose of this task is to write precise definitions for the three rigid motion transformations and to represent images produced by translations, reflections, and rotations as functions of their pre-image. By the end of this task, you should be able to precisely define translation, reflection, and rotation, and write a function rule to represent specific translations, reflections, and rotations. In part 1 of the task, the students wrote formal definitions of the three rigid motion transformations that Carlos and Clarita will be using to create the images for the flip book animation. The students completed the sentence for question number 1. A translation of a set of points in a plane is the movement of all points the same distance and direction along lines that are parallel to each other. For question 2, they completed the sentence for a rotation. A rotation of a set of points in a plane is the movement of all points the same direction along concentric circles and through the same angle of rotation. For question 3, the students defined reflection. A reflection of a set of points in a plane is the movement of all points across a specified line of reflection, so that the line of reflection is the perpendicular bisector of each line segment connecting corresponding pre-image and image points. For the final statement, the students defined rigid transformations. Translations, rotations, and reflections are rigid motion transformations because the distance and angle measures within the shape are preserved. In part 2 of the task, Carlos and Clarita want to include an image in the flipbook. They also want to include definitions of transformations that are symbolic. In the text, we are introduced to the function rule notation for a translation. In the previous tasks, we used a mapping rule to show the ordered pairs of the input are mapped to the ordered pairs of the output using the rule. In this task, Carlos and Clarita have used a function rule. A function rule is an algebraic rule that represents the transformation which produced the image as a function of the pre-image. For problem number 1, we have been asked to compare the ordered pairs for the February 28th house to the ordered pairs for the February 29th house. This house has been reflected over the line y equals negative x. By comparing the ordered pairs of the pre-image to the corresponding ordered pairs on the image, we're going to look for a pattern that we can use to write a function rule to represent the reflection over the line y equals negative x. The first step in determining the pattern is to list the ordered pairs of the pre-image points and show the mapping to the corresponding ordered pairs for the image points. Here in blue, I have listed the pre-image ordered pairs, and in purple, the corresponding image ordered pairs. The point negative 7, 3 mapped to the ordered pair negative 3, 7. This was on the side of the house with the roof with no chimney. You can see that the house flipped over the line. The ordered pair negative 6, 0 mapped to the ordered pair 0, 6. This was down at the yard by the door. Negative 4, 4 stayed exactly in the same location because it was located on the line of reflection. The ordered pair negative 3, 1 mapped to negative 1, 3. Now that we have the ordered pairs mapped from the pre-image to the corresponding image points, we can look for a pattern. If we look at -7, 3 mapped to -3, 7, we can see that the x and y positions of the ordered pairs switch places. The -7 was in the x position, became a +7 in the y position. The 3 in the y position became a -3 in the x position. We can represent this transformation using the function rule f of xy equals -y -x. The function rule can be applied to the other sets of pre-image and corresponding image points. -6, 0 mapped to 0, 6. The -6 from the x position became the y position and opposite, and the 0 moved to the x position. With an ordered pair that contains 0, it can be a bit more challenging to find the pattern since 0 does not show a sign change. The function rule can also be applied to the last two ordered pairs. When you're looking for a pattern, an ordered pair such as -4, 4 mapping to -4, 4 can be challenging since both the x and the y coordinates had the value of 4. This can make it difficult to see the switch in positions of x and y. For problem 2, we were asked to use the March 1st house to complete a reflection over the line y equals x. We will use patty paper to help us determine where the image of the March 1st house should be located. So on the patty paper, I've traced the x-axis and the y-axis along with the line of reflection y equals x. We're going to flip the house over the line y equals x. Notice that the ordered pair 4, 4 mapped to 4, 4. This point did not move since it was located on the line of reflection. The ordered pair 7, 3 mapped to the ordered pair 3, 7. The ordered pair 3, 1 mapped to the ordered pair 1, 3. 6, 0 mapped to the ordered pair 0, 6. If we were to connect the pre-image points with the corresponding image points, we could see that the segments created are perpendicular to the line of reflection and that the line of reflection bisects the segments. When we are trying to write a rule, we need to look for the pattern of what happened to the x's and the y's during the transformation. When we look at ordered pair 7, 3 mapped to 3, 7, it appears as though the x and the y positions switched. If we try to apply that rule to 3, 1, we see that it works because it became 1, 3. The x and y positions switched. So the function rule for reflection over the line y equals x is f of xy equals y x. For problem number 3, we were asked to reflect any house over the x-axis. We chose to reflect February 28th over the x-axis. The students began by writing the ordered pairs for the pre-image mapped to the corresponding ordered pairs for the image. Negative 6, 0 mapped to negative 6, 0. This is because negative 6, 0 is located on the x-axis, which is the line of reflection. Negative 3, 1 mapped to negative 3, negative 1. This mapping reveals that the x value of the ordered pair stayed in the same position and kept the same sign. The y value stayed in the same position, but seems to have become opposite. We can write the function rule to represent this transformation as f of xy equals x negative y. The application of this transformation rule maps every point of the input, or the pre-image, to the specific corresponding points of the output, or the image. The function rule for reflecting over the x-axis is f of xy equals x negative y. For problem number 4, we were asked to select a house and reflect it over the y-axis. We selected February 28th. We recorded the pre-image coordinates for February 28th and used patty paper to reflect February 28th over the y-axis. February 28th mapped to March 1st. When we look at the ordered pairs, it seems that the x values became opposite, and the y values remained the same. We can use the function rule f of xy equals negative xy to represent the reflection over the y-axis. For problem number 5, we were asked to compare the March 1st house to the February 29th house. We were told that a 90-degree counterclockwise rotation about the origin occurred. If we compare the ordered pairs in blue for the pre-image to the ordered pairs in purple for the image, we can see a change in position of the x and y ordered pairs. 7 was in the x position, became a 7 in the y position. The 3 in the y position moved to the x position. Additionally, in this ordered pair, we can observe that the 3, which was in the y position, changed signs when it moved to the x position. We can write the function rule f of xy equals negative yx to represent this transformation. For problem 6, we were asked to examine a 180-degree rotation about the origin, as well as a 90 degrees clockwise rotation about the origin. We took the February 29th house and rotated it 180 degrees about the origin. It's not necessary to provide a direction with 180 degrees, since 180 degrees clockwise is equivalent to 180 degrees counterclockwise. The 180-degree rotation of February 29th mapped onto this house in the 4th quadrant. When we compared the pre-image ordered pairs with the corresponding image ordered pairs, we were able to generate the rule f of xy equals negative x, negative y. The second part of the question asks us to perform a 90-degree clockwise rotation about the origin. We used the same house, February 29th, and used patty paper to rotate it 90 degrees clockwise. A 90-degree clockwise rotation is equivalent to 270 degrees counterclockwise. After comparing the corresponding pre-image and image coordinates, we were able to generate the rule f of xy equals y negative x. From this task, you should have been able to write function rules for reflections and rotations about the origin. Let's quickly review the rules. For a reflection over the x-axis, the y value becomes opposite. For a reflection over the y-axis, the x value becomes opposite. If a figure is reflected over the line y equals x, the x and the y values change positions. If a figure is reflected over the line y equals negative x, the x and y values switch positions and both change signs. Let's review the function rules for rotations about the origin. It is important to note that these rules only apply to rotations about the origin and not to rotations about points in the coordinate plane other than the origin. For a 90-degree counterclockwise rotation, which is equivalent to a 270-degree clockwise rotation, the function rule is f of xy equals negative y x. For a rotation of 180 degrees, the function rule is f of xy equals negative x, negative y. For a 270-degree rotation counterclockwise, or 90-degree clockwise, the function rule is f of xy equals y negative x. This concludes the summary video for the task Leap Year. If you need more help on the Ready, Set, Go homework for this task, please remember to check the Canvas Student Support site.